Hi everybody. Today we are going to finish a couple of topics in section 9.1 and then complete the topics in section 9.2. We are still discussing moments of inertia, and in lecture 23 we discussed using direct integration to find moments of inertia about an x or y axis. So today we're just going to finish our discussion by talking about what is a polar moment of inertia, or a moment of inertia about a point, and also a mathematically calculated distance called a radius of gyration, which has to do with, it's a mathematical concept that dovetails into the idea of moments of inertia. The most important thing to remember is, in order to find any of these quantities, unless you are using composite shapes, one way to do it, and generally the best way to do it, is to find I sub x and I sub y, and then the calculations for polar moment and also radii of gyration fall into shape. So going over to the document cam, we will get started talking about these ideas. And I made myself some notes so I would not forget to talk about the polar moment of inertia yet again. So in the last pieces of section 9.1, we talk about this idea of a polar moment of inertia. And then we talk a little bit about radius of gyration. What these are, a polar moment of inertia, is if we have a shape, for example, if this is our x-axis and this is our y-axis and this is our origin, if we have some sort of a shape, it does not matter if it intersects an axis or not, but if it's, like, let's just say this general shape, if we find I sub x and I sub y, the polar moment of inertia, which is they use the variable j to describe the polar moment of inertia, and then they always put a sub-zero indicating the point that you're taking it about. So you could take a polar moment of inertia about other points, but basically in this case, if we have I sub x and I sub y, and they are the axes, that's the intersection of those 2 points, turns out that the polar moment of inertia is equal to I sub x plus I sub y. So that's pretty simple if you find I sub x and I sub y first. So the first job to do is to do what we did last time, or the method that we're going to use today if we have a composite shape, to find I sub x and I sub y, add them together, not even vectorially, just arithmetically, and you would have the polar moment of inertia. So for example, if my I sub x value was 43 inches to the fourth, and my I sub y value was 71 inches to the fourth, my j sub o would be equal to the arithmetic sum of those 2, inches to the fourth. So it has the same units and the same dimensions, and it's just the arithmetic sum of I sub x and I sub y. Well, in section 9.1 part D, we talk about an idea of something called the radius of gyration. And basically, the concept of radius of gyration is that an area A has some moment of inertia I sub x with respect to the x-axis. And if we were to concentrate that area, like this, into a teeny strip, it's odd to think about concentrating an area, but if we think about it as concentrating it into a teeny strip, some distance from the x-axis, the radius of gyration would be that distance to the strip. So the radius of gyration, once again, just like the polar moment of inertia, the radius of gyration has to be defined about an axis. So in this case, if we had, and they used the letter k to define radius of gyration, k sub x is the radius of gyration about the x-axis. K sub y is equal to the radius of gyration about the y-axis. So for example, if this area were concentrated into a little strip, so this would be k sub x, this would be k sub y, Okay? And then we also have a K sub 0, which is the concentrated intersection of those strips, or the dot, the tiny little area about the center. So primarily, they are mathematical concepts, but you can calculate them. You can go backward. If you think about this, I sub x is usually some sort of a y squared dA. So in this case, we're going to say it's a k sub x times a. So that means that k sub x is going to equal the square root of I sub x over a. K sub y then must be I sub y over a. And last but not least, k sub 0 is square root of j sub 0 over a. So they're easy to calculate if you, in fact, have the formulas. The other thing is that k sub o, if you have your radii of gyration about the other two axes, you can use the Pythagorean theorem to find them. You can see we have a little triangle action going on here. Right triangle. All right, so if you look at the units, it should be a distance. This would be length to the fourth over length squared, which cancels to length squared as the radicand. When you take the square root of length squared, it's length. And the same is true here and here. So the radius of gyration has dimensions of length. The polar moment of inertia has dimensions of length to the fourth, just like the x and y moments of inertia. All right, now if you recall, we're going to move on to section 9.2. And if you recall, when we were doing first moments, or we were doing q's, q sub x and q sub y, we talked about q's using composite areas first, and then we talked about finding q's by direct integration. When we talked about moments of inertia, we did direct integration first. And the reason for that is because we wanted to have some information about that axis in order to discuss something called the parallel axis theorem. Now, if you recall, we had said that the moment of inertia of an object with some shape is never equal to 0, but that it is a minimum about the centroid, about the objects or the shapes centroid. Well, what if you don't want to take the moment of inertia about an object centroid? In other words, if you have a box like this, a rectangle, and instead of taking it about the centroid here, you want to take it about the x-axis. This would be called I sub x bar, which just the bar above the I indicates that it's centroidal, and the I sub x means about the x-axis. Well, the answer is that you can use something called the parallel axis theorem to find I about any axis parallel to the centroidal axis. And what it looks like is this, is that I sub x is equal to I sub x bar plus a times d squared. D is the distance from the centroidal axis to the new axis, or the axis in question. So in other words, this term is always the centroidal moment of inertia. This distance is the distance from the centroidal axis to this axis, wherever it is, and then area is the area of the shape. And this has, of course, units of length to the fourth, dimensions of length to the fourth, as does this. So what we're saying is, if we wanted to get the moment of inertia of a rectangle about its base, we could say that that's going to equal the centroidal moment of inertia of that rectangle plus the area of the rectangle times the distance between this and this squared. we can use the parallel axis theorem similarly. If we have some shape that looks like this, and we have the centroidal axis known, and we want to take it about this axis, we know that this would be D, so we have the same thing. We can find I sub x bar plus the area of the rectangle times this distance squared. So it's very useful in the sense that if we have centroidal axes, or if we could even tabulate centroidal moments of inertia, or we could tabulate centroidal moments of inertia, we could then just take the area and the distance between the centroidal axis and whatever axis we want and compute the moment of inertia about that axis. Works exactly the same about the y-axis. Centroidal, distance, there you go. All right, so the other powerful piece in section 9.2 is a table. This is also probably on the inside cover, back cover of your book, inside or outside back cover of your book. But basically, you'll see we have tabulated. I'm going to go ahead and telescope in on this so you can see a couple, maybe a little better. And over here, we have some of those moments of inertia. Now, it's important to note, when you have a bar, that means centroidal. So that means about this axis, and then in the y direction this. Now you'll notice here it says I sub x bar prime, I sub y bar prime. This is called x bar and y bar, so that's really redundant. It's just reminding you this means it's about the centroidal axis. X bar down here, y bar over here, and then the polar moment j sub c, which is right here, is equal to this. But we could find I sub x bar, I sub y bar, use the parallel axis theorem to find I sub x and I sub y, and then we could find the moment about the point 0 in this case. Okay, triangles, same thing. Here we have I sub x prime, so we have this, and then we have I sub x, which would be about this axis. And if you look at these two, it would turn out that this plus the area of the triangle times the distance between those two things squared will be equal to this. Okay, then we have a circle, semicircle, a quarter circle, and an ellipse. All right, well, one of the big things that we can use this idea for is to find the moment of inertia of composite shapes. Because if we have a shape that is made up of pieces that we could tabulate about their own centroids, we could then use the parallel axis theorem to tabulate about the centroid of the object. Okay. So, for example, here on 9.1, I'm going to work this problem. It says determine the moment of inertia and the radius of gyration of the shaded area with respect to the x-axis. Okay, so if you see this is sort of an I-beam, it's an unequal, non-symmetrical I-beam. So we could think of this as being three different rectangles. The footing rectangle, the web rectangle. These are called flanges. This is called a web. So there's a web, two flanges. We have the lower flange, the inner web, and then the upper flange. Each one of those is a rectangle, and we know from our table what the moment of inertia of each of those is about their own centroid. So then if we can determine the distance between the centroid of this flange about this axis, x, we can use the parallel axis theorem. Same for the web, same for the bottom flange. All right, so let me show you how that works. I would really like to kill that little light, but it just wants to keep coming through the blinds. Okay, well, let's take a look. We have a non-symmetric I-beam that looks like this. Oops, better get that on the screen. There we are. All right, we're told this is the y-axis, this is the x-axis, and we call the point of intersection O. These distances are each 24 millimeters. The height of the bottom flange is 6 millimeters. The web is 8 millimeters thick, and it's 24 and 24 millimeters. So a total of 48 millimeters. And then my top flange, 12 and 12. I'm just going to put dimensions in millimeters, so I don't have to keep writing millimeters over and over again. And then it is also 6 millimeters high. Okay? All right. So what I'm going to do is to think of this as being 3 pieces. 1, 2, and 3. Each one of those is a rectangle. So I know that I sub x bar, in other words, the centroidal moment of inertia, from my chart that I had on the screen just a second ago. I know that the centroidal moment of inertia value is 1/12 times the base times the height to the third. So I sub x of 1 is going to be 1/12 times the base, which is 24 millimeters, times the height to the third power. I sub x2 is equal to 1/12 times the base times the height to the third power. And I sub x3, about its centroid, is 1/12 times the base times the height to the third power. Right. So I sub x bar of 1 is 6 to the third power times 24 divided by 12, which is 432 millimeters to the fourth power. Here I have 48 to the third power times 8 divided by 12. So that I sub x2 is 73,728 millimeters to the fourth. And then I sub x bar 3 is 48 times 6 to the third power divided by 12, which is 864 millimeters to the fourth. Okay, now I have the centroidal moment of inertia of each of my 3 composite shapes, but I want to move them to this axis. So I have to add to that AD squared, because I about x is going to be equal to I sub x bar plus AD squared. All right, so I need to figure out what distance is for each of these. So for the first one, I'm going to have plus my area, which is just height times width. But now I need to compute the distance. Well, the distance from here to the base of 1 is 24, but 1 is actually 6 millimeters wide. So its centroid, because it's a rectangle, is right in the middle. So it's 3 millimeters up, so it's 3 plus 24, which is 27. That's the distance squared. Now for 2, the centroid of 2 is at the centroid of, or as at the x-axis. So this is going to be plus something times 0 squared, because the distance is 0. So that term contributes nothing to the final calculation. And then the bottom, we have the area, which is 48 this way, 6 this way. And then what's my distance? 24 plus 3, which is 27 again, and I square it. So the other thing you need to notice is whether something is above or below the centroid. This is the centroid, but there's no really, we haven't really proved that that is at the centroid. It wouldn't matter. It could be at any axis. But whether something is above or below the axis of rotation, it always contributes positively to the moment of inertia because it's non-directional in the sense that we're talking about spins. So something above and something below both increase the moment of inertia. All right, so for my first term, I have 27 squared times 6 times 24, and I add to that my centroidal moment, or centroidal moment of inertia, 432. So that value is 105,408, once again in dimensions of millimeters. This contributes the parallel axis theorem. Does not contribute anything because the centroidal moment, the centroidal axis of part 2 is the centroidal axis given by x. And then last but not least, we're going to take 27 squared, multiply that by 6, multiply it by 48, and add that to the centroidal moment of inertia part 3, 864, and that value is 210,816. All right, so I sub x of all three of these, of this composite shape, is equal to this number plus this number plus this number. And that is 389,952, and the units are millimeters to the fourth. All right, so for problem 1, we have now used the parallel axis theorem to move that value to a different axis. All right, it says determine the moment of inertia and the radius of gyration. All right, so when we just talked a little bit today about the radius of gyration, what we would be talking about is a k sub x. So k sub x, the radius of gyration about the x-axis, is equal to the square root of the moment of inertia about that axis divided by the area. So we have the value of I sub x. We need to compute our area. So the area is, the top piece is 24 times 6. Oops, 24 times 6. The middle piece is 8 times 48. And the bottom piece is 48 times 6. So the total area of this shape is 24 times 6 plus 8 times 48 plus 48 times 6. And that entire area is 816. Everything was measured in millimeters, so this is going to be millimeters squared. So coming back over here, radius of gyration then is equal to the square root of 389,952 millimeters to the fourth over 816 millimeters squared. So my radicand is, let's find my 1 over, multiply that by 389,952. So my radicand is 477.9 millimeters squared, because millimeters to the fourth divided by millimeters squared is millimeters squared. So when I take the square root of millimeters squared, I'm going to end up with millimeters, and the value is the square root of that, 477. And my calculator tells me that that is 21 millimeters. So what that means is that we have a radius of gyration, which is 21 millimeters right under here or right under here from the x-axis. That is going to be where, if we concentrated the mass at that point, what the radius would give us an equivalent moment of inertia. All right, everybody. So that's it for today. I will assign you a couple of problems that involve the ideas of radius of gyration, polar moment of inertia, which is just adding two together, and then using the parallel axis theorem. So we will see you next time for our continuing discussion on Chapter 9.